Ever wondered why the universe doesn't behave the way you expect it to? Welcome to the world of quantum mechanics. Quantum mechanics, my friends, is not your average science. It's a branch of physics that throws our everyday understanding of the world out the window, replacing it with ideas that are as fascinating as they are mind-boggling. We're talking about particles existing in multiple places at once, cats that are both alive and dead, and particles that can teleport through impenetrable walls. Yes, it's a wild ride, but what exactly is quantum mechanics? It's a theory that describes the fundamental nature of the universe at the smallest scales of energy levels of atoms and subatomic particles. It's the science of the very small, the very high-tech, and the very strange. Now you might ask, why should I care about quantum mechanics? Well, without quantum mechanics, we wouldn't have many of the technologies we rely on today. Everything from your smartphone to your computer, from GPS systems to MRI scanners, owes its existence to the strange and wonderful world of quantum mechanics. But let's not forget, quantum mechanics is notoriously counterintuitive. It's a world where the rules of classical physics cease to apply, where particles can act like waves, and waves can act like particles, where the act of observing can change the outcome of an event. It's a world that challenges our understanding of reality. Here's the kicker. Even though quantum mechanics is over 100 years old, it's still a hot topic of research. Scientists around the globe are still trying to unravel its mysteries and harness its power. From quantum computing to quantum teleportation, the possibilities are endless and the potential is enormous. So, buckle up, because we're about to dive into this fascinating realm. A realm where our everyday logic is turned upside down, where the conventional becomes unconventional, and the impossible becomes possible. We're about to explore a world that is far stranger and far more wonderful than anything you could possibly imagine. Prepare to enter a realm where the impossible becomes possible. Imagine a world where particles can be in two places at once. Welcome to the quantum realm, where the building blocks of matter behave in ways that defy our everyday logic. Let's start with the fundamental particles in quantum mechanics: electrons, photons, and quarks. Electrons, those tiny negatively charged particles that orbit the nucleus of an atom, are quantum entities. They exhibit a behavior known as wave-particle duality. This means that electrons can behave as particles, located at a specific point in space, or as waves, spread out over a range of possible locations. They switch between these states depending on whether they are observed or not. Photons, the particles of light, also exhibit this duality. They can behave as particles, moving in a straight line, or as waves, spreading out and interfering with each other. This is what gives rise to phenomena such as diffraction and interference, where light can bend around corners or create patterns of bright and dark bands. Then we have quarks, the particles that make up protons and neutrons in the nucleus of an atom. There are 6 types of quarks, each with its own unique properties. They are always found in combinations, never alone, due to a phenomenon known as color confinement. But what's truly mind-boggling is the concept of wave-particle duality. It's like saying that a football can be in 2 places at once, or that a wave on the ocean can suddenly become a single drop of water. This is a radically different way of understanding the nature of matter, one that challenges our everyday experiences and intuitions. Yet, it's this very duality that lies at the heart of quantum mechanics. It's what allows quantum computers to process vast amounts of information simultaneously, or quantum tunneling to occur, where particles can pass through barriers that should be insurmountable. In the quantum world, particles aren't just particles, they're waves too. This is the fascinating world of quantum mechanics, where the building blocks of our universe play by a different set of rules. Buckle up for the ride as we delve deeper into this intriguing realm. Scene script. Can we know both the speed and location of a particle simultaneously? Think again. Welcome to the realm of quantum mechanics, where the seemingly impossible becomes possible, and certainty gives way to probability. Our guide for this journey is Werner Heisenberg, a Nobel laureate physicist, who introduced us to the uncertainty principle. The Heisenberg uncertainty principle is a cornerstone of quantum mechanics. It tells us that we can't know both the position and momentum of a particle with absolute precision. The more accurately we know one of these values, the less accurately we know the other. To grasp this concept, imagine trying to find a tiny, speedy electron in a vast universe. You might be able to determine its speed quite accurately, but it would become increasingly blurry and uncertain where exactly it is. Conversely, if you pinpoint its exact location, its speed becomes a blur. This isn't due to any shortcomings in our measurement tools. It's a fundamental aspect of nature itself. Particles at the quantum level exist in a cloud of probabilities, not definite states. The act of measuring disturbs the system, changing the outcome. This principle has profound implications for our understanding of the universe. It challenges the deterministic view of the world, where everything follows predictable laws. Instead, it presents a universe ruled by probabilities, where certainty becomes an illusion. The uncertainty principle also gives rise to some of the most mind-bending phenomena in quantum mechanics, like quantum tunneling and superposition, which we'll explore in the coming scenes. Before we leave the uncertainty principle, let's take a moment to appreciate its beauty. It's a testament to the ingenuity of human thought, our ability to explore and understand even the most elusive aspects of our universe. It also reminds us of the inherent mystery and wonder of the world we live in, where the more we know, the more questions we uncover. What if something could be in two states at the same time? Now, this might sound like the premise of a science fiction novel, but in the realm of quantum mechanics, it's not only possible but a fundamental principle known as superposition. Quantum superposition tells us that a quantum system can exist in multiple states simultaneously. It's a bit like flipping a coin. The moment before it lands, the coin is in a superposition of states. It could be heads, or it could be tails. It's only when the coin lands, the moment we observe it, that it chooses a definite state. But let's make this concept a bit more tangible with a classic thought experiment, Schrödinger's cat. Imagine a cat inside a box with a radioactive atom. If the atom decays, it triggers a mechanism that releases poison, and the cat dies. If it doesn't decay, the cat lives. Now, according to classical physics, the cat is either alive or dead. But in the quantum world, until we open the box and observe, the cat is in a superposition of states. It's both alive and dead. Strange, isn't it? But Schrödinger's cat isn't just a bizarre thought experiment. It's a powerful metaphor for superposition, illustrating how quantum particles can exist in multiple states until they are observed. This concept is not only fundamental to quantum mechanics, but also forms the basis of many emerging technologies, including quantum computing. So the next time you flip a coin, remember that until it lands, it's not just heads or tails. It's in a state of superposition. It's both heads and tails. And the next time you see a cat in a box, well, you get the idea. Remember, in the quantum world, nothing is certain until observed. Until you look, everything is a possibility. Can two particles be intimately connected, no matter how far apart they are? This question introduces us to the phenomenon of quantum entanglement, one of the most intriguing aspects of quantum mechanics. Imagine two particles, born together and then separated. Despite being light years apart, changes to one particle instantly affect the other. This is not because of any signal passing between them, but because they are entangled. Their properties are not independent of each other. They're intertwined, linked in a way that transcends ordinary spatial constraints. This is not some fanciful theory, but an empirical reality, confirmed by numerous experiments. It's as if the universe has a hidden layer of connections, invisible threads that bind particles together. This is what Albert Einstein famously called spooky action at a distance. He was troubled by it, as it seemed to violate the principle of locality, the idea that an object can only be influenced by its immediate surroundings. Yet, quantum entanglement holds true. It's not just a curiosity of the quantum world, but a fundamental feature. It's a testament to the fact that the universe at its core level operates on principles that are far removed from our everyday experiences. But why should we care about quantum entanglement? Well, it's not just about understanding the universe better. Quantum entanglement has practical implications as well. It's the foundational principle behind quantum computing, a technology that could revolutionize our world. Imagine a computer that could solve problems in seconds which today's fastest supercomputers would need centuries to crack. That's the power of quantum computing, and it's all thanks to quantum entanglement. So step back and marvel at this remarkable aspect of the quantum world. It challenges our intuition, forces us to rethink our understanding of reality, and opens up new technological possibilities. Quantum entanglement is more than a scientific oddity. It's a window into the deep, interconnected nature of the universe. Welcome to the spooky action at a distance that Einstein found so troubling. But remember, sometimes the most profound truths are the ones that trouble us the most. What if you could walk through walls? Quantum particles can. Now, that might sound like a line straight out of a science fiction novel, but it's actually a well-established phenomenon in the realm of quantum physics, known as quantum tunneling. Let's consider a classical scenario first. Imagine a ball trying to roll over a hill. If the ball doesn't have enough energy to get over the hill, it's stuck. It rolls back the way it came. That's the world as we understand it. But quantum particles, they don't play by these rules. They have a knack for doing the impossible. Quantum tunneling is the process where particles penetrate a barrier that they shouldn't be able to, at least not according to classical physics. It's like our ball suddenly appearing on the other side of the hill without ever having climbed it. This isn't due to an increase in energy, but rather the inherent uncertainty that comes with quantum particles. This quantum uncertainty allows particles to exist in a superposition of states, and their wave function, a mathematical description of the quantum state of a system, can extend through barriers. Even if the particle doesn't have enough energy to classically pass through, there's still a non-zero probability that the particle can tunnel through the barrier. This isn't just a theoretical concept either. Quantum tunneling has real-world implications. It's responsible for a variety of phenomena, from the nuclear fusion that powers the sun to the operation of quantum computers. In the grand scheme of quantum mechanics, tunneling is just one of the many ways that quantum particles defy our everyday intuition. It's a testament to the strange and fascinating rules that govern the quantum realm, where particles can be in two places at once, become entangled over vast distances, and yes, even tunnel through impenetrable barriers. In the quantum world, barriers are just suggestions. How can quantum mechanics revolutionize computing? Let's explore. Quantum mechanics, with its strange but fascinating principles, can give birth to a new era of computing. Quantum computing, a concept that might seem like a plot from a science fiction novel, is actually a reality in the making. But what exactly is it? Unlike classical computers that use bits for processing information, quantum computers utilize quantum bits or qubits. These qubits are special because they can exist in multiple states at once, thanks to the principle of quantum superposition. This means that a quantum computer can process a vast amount of information simultaneously, making it exponentially faster and more efficient than its classical counterpart. Now let's add another layer of quantum weirdness. Recall quantum entanglement, the phenomenon where particles become interconnected, and the state of one can instantly affect the other, regardless of distance. This principle is also employed in quantum computing, allowing for a level of synchronization and communication between qubits that's simply not possible in classical computing. So how does this translate into potential? Imagine solving complex problems that would take classical computers centuries to crack in a matter of seconds. Quantum computing could revolutionize fields like cryptography, materials science, medicine, and even artificial intelligence. However, don't get too excited just yet. Quantum computing is still in its infancy. There are significant challenges to overcome, such as maintaining qubit stability and managing quantum decoherence. But scientists and researchers around the globe are tirelessly working to make quantum computing a practical reality. Even with these challenges, the potential of quantum computing is undeniable. It's like we're standing at the edge of a new frontier, one that's ripe with possibilities, waiting to be explored. Quantum computing could be the next big revolution in technology. How does quantum mechanics challenge our understanding of reality? This is a question that has perplexed scientists and philosophers alike for the better part of a century. Quantum mechanics, the reigning theory of the micro-world, is notorious for its oddities. It's a realm where particles can be in two places at once, where they can tunnel through impenetrable barriers, and where measurement can fundamentally alter the state of a system. In the macro world we inhabit, we're used to a reality that follows a deterministic rulebook. Drop a ball, and it falls. But in the quantum world it's a different story. The ball might fall, or it might not. It might even do both at the same time. This probabilistic nature of quantum mechanics is in stark contrast to our everyday experiences, shaking the very foundations of our understanding of reality. Let's consider the famous double-slit experiment. When particles of light, or photons, are fired one by one at a screen with two slits, an interference pattern emerges. as if each photon is going through both slits at once and interfering with itself. But observe which slit the photon goes through, and the interference pattern disappears. This is a clear example of how observation in the quantum world can fundamentally alter the outcome. Then there's the phenomenon of quantum entanglement, where particles become intrinsically linked, such that the state of one instantaneously affects the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, defies our everyday understanding of space and time. Quantum mechanics, in essence, forces us to reconsider our notions of reality. It tells us that the world is not as concrete and predictable as it seems. Instead, it's a fuzzy, interconnected web of probabilities and possibilities. It's a reality that's deeply counterintuitive, yet undeniably real according to our best scientific understanding. Quantum mechanics shows us that reality is far stranger than we could have ever imagined. Scene script: Quantum mechanics, a world where the impossible becomes possible. We've taken a fascinating journey, haven't we? We started off by grappling with the very concept of quantum mechanics, exploring the realm of the atomically tiny, where particles can exist in two places at once and pop in and out of existence. We delved into the building blocks of quantum mechanics, the quantum particles, the smallest constituents of the universe. We learned that these particles don't behave like anything we're familiar with in our everyday world. They can be in multiple states at once. They can teleport through barriers, and they can even influence each other instantaneously over vast distances. We then ventured into the world of uncertainty, where precision is not a possibility, but rather a luxury. The Heisenberg uncertainty principle taught us that we cannot know both the position and momentum of a particle with absolute certainty. The more precisely one measures one quantity, the less precisely the other can be known. Next, we explored the mind-boggling phenomena of superposition and entanglement. Quantum superposition allows particles to exist in multiple states at once, only deciding their state when observed. Quantum entanglement, on the other hand, creates an inseparable bond between particles. Change the state of one, and its entangled partner responds instantaneously, no matter the distance. Quantum tunneling showed us that particles can pass through barriers as if they were not there. This concept is crucial in the functioning of many modern technologies, like the scanning tunneling microscope. We then progressed to quantum computing, where qubits can hold more information than classical bits, promising us a future of incredibly powerful computers. And finally, we looked at how quantum mechanics impacts our understanding of reality itself. It challenges our intuition, our concepts of cause and effect, and even our perception of time and space. Next time you think about the universe, remember, it's a quantum world.